Your body has a kill switch. It was designed and armed before you were even born. Every moment of your life is run by a clock that's relentlessly ticking down. We see it in the mirror. We feel it in our bones. We call it aging, and we tend to accept it as just the way things are. But what if it isn't? What if your body isn't failing because it's broken? What if it's failing because it's following a script? A set of instructions written into your DNA, not for your benefit, but for the benefit of ancestors who have been dead for 100,000 years. The reason you age and die is a brutal evolutionary trade-off. It's a ghost in your genetic machine. Tonight, we're going to find that ghost. We'll uncover why evolution, the very force that's supposed to be all about survival, seems completely indifferent to you dying. And then we'll step into the terrifying, thrilling world that could exist if we finally learn how to exercise it for good. To solve this mystery, we have to understand the crime. And the crime scene is your own body. Why would a process like natural selection, which is so focused on survival, build a system that's basically designed to fall apart? It feels like a paradox, like a car company designing a car that's guaranteed to rust, or a software developer programming an app that's meant to crash. The answer is that evolution isn't playing the long game. It has one single, ruthless priority: get your genes into the next generation. That's it. Anything that helps you survive long enough to have kids is a win. But from an evolutionary point of view, whatever happens after that is mostly just an epilogue. Classical evolutionary theory suggests that aging happens because natural selection just doesn't have much of a reason to care about us as we get older. Think about it like this. In the world of our ancient ancestors, life was often short and dangerous. You were way more likely to be killed by a predator, a famine, or an infection than you were to die of old age. Life expectancy at birth was low, mostly because so many children didn't survive. Now, if you made it through childhood, you could live for several decades, but the world was still a risky place. So, evolution placed all its bets on youth. It built the human body to be a peak performance machine for the first few decades of life. It needed you to be strong, fast, and fertile now, not in 50 years. The genes that made you grow quickly, gave you a powerful immune system, and fueled your reproductive drive were the ones that got passed on. But any genetic glitches that caused problems later in life, say at age 60 or 70, were largely invisible to natural selection. Why? Because far fewer people lived long enough to experience them. Those late-acting harmful mutations were hidden in what biologists call the selection shadow. So your long-term survival was traded for your ancestors' short-term reproductive success. Your body wasn't designed to last forever. It was designed to win one single critical race, and after that, it was considered disposable. This idea of a trade-off is the key to the whole mystery of aging. And it's not just a theory, it's a real biological mechanism. In the 20th century, biologists gave it a name: antagonistic pleiotropy. It sounds complicated, but the idea is brutally simple. Pleiotropy just means a single gene can do more than one thing. Antagonistic means those effects can work against each other. So, an antagonistically pleiotropic gene is one that gives you a benefit early in life, but comes with a hidden cost you have to pay later. Imagine a gene that makes your cells grow and divide quickly. When you're young, that's fantastic. It helps you heal from injuries faster, build strong muscles, and grow up. Evolution loves this gene because its early life benefits are a huge advantage. But what happens when that same gene is still active in your 50s, 60s, and 70s? Uncontrolled cell growth is the very definition of cancer. The gene that helped you thrive as a young adult could be the one that helps kill you as an old one. This principle is everywhere. Genes that create a strong inflammatory response to fight off infections in your 20s can lead to the chronic body-wide inflammation that causes heart disease in your 60s. Genes that help you build strong bones by managing calcium can later contribute to that same calcium hardening your arteries. Evolution filled your body with these kinds of deals. It made a bargain for your youthful energy. And the price is your eventual decline. This is backed up by another related idea called the disposable soma theory. Your soma is your physical body, everything that isn't a reproductive cell. The theory suggests that every organism has a limited budget of energy. It can spend that energy on two things: keeping the body repaired or making babies. Because the chances of dying from, say, a falling rock or a hungry lion were so high, it just didn't make evolutionary sense to invest tons of energy into building a perfect body that could last forever. It was a better bet to use that energy to reproduce. So your body, the soma, was treated as disposable. Once the genetic information was passed on, the container it came in was no longer the priority. It was left to rust. These two theories aren't fighting each other. They're two sides of the same coin. They paint a chilling picture. Your aging isn't an accident. It's the predictable result of an evolutionary strategy that cared more about your ancestors having kids than about you living forever. So, if evolution wrote the script, how does the body actually act it out? What's happening on the inside? For a long time, scientists saw aging as a big, chaotic mess of things going wrong. But recently, they've organized that chaos into a framework called the hallmarks of aging. There were originally 9, but the list was updated and expanded to 12 in 2023. Think of them not as separate problems, but as a tangled web of decline. First, the blueprint itself gets corrupted. This includes genomic instability and epigenetic alterations. Your DNA is your body's master plan. Over time, it collects typos and errors. That's genomic instability. But just as important are the epigenetic alterations. If DNA is the cookbook, the epigenome is the chef who decides which recipes to cook. As we age, the chef gets confused. Genes that should be off get turned on, and vice versa, causing cells to forget what they're supposed to do. Next, you get cellular zombies. This is a hallmark called cellular senescence. As cells get damaged, some of them stop dividing but refuse to die. These senescent cells are like zombies that hang around in your tissues, leaking out a cocktail of inflammatory junk that damages the healthy cells around them. This creates a low-grade chronic inflammation throughout your body, another hallmark that's linked to almost every age-related disease. Then there's the power failure. Your cells are powered by tiny engines called mitochondria. Mitochondrial dysfunction is the hallmark that describes how these power plants get rusty and inefficient. They produce less energy and spit out more damaging waste, creating a vicious cycle of more damage and less energy to fix it. This is a big reason why people feel less energetic as they get older. And finally, the whole communication network breaks down. This is called altered intercellular communication. Hormonal signals get scrambled. The immune system gets weaker at fighting germs, but more likely to attack the body itself. It's like a city where the phone lines, the power grid, and the police force are all failing at once. The key thing to understand about the hallmarks is that aging isn't one thing. It's everything, everywhere, all at once. You can't just fix one and hope to stop the whole process. It's an intricate domino effect of failure. So how do you get rid of a ghost that's woven into every cell of your body? For the first time, we're starting to get a real scientific answer. The goal is no longer just extending lifespan, but extending health span, the number of years we spend in good health. And researchers are now trying to attack the hallmarks of aging directly. We have experimental drugs called senolytics that are designed to hunt down and destroy those zombie senescent cells. We have research exploring how to polish the epigenome, resetting it to a younger state. And in a major step, the first FDA-cleared human trial of a partial epigenetic reprogramming therapy began in early 2026. The Life Biosciences ER100 program is a phase 1 safety study designed to treat specific eye diseases by targeting aging mechanisms. It's not a cure for aging, but it's a monumental first step towards seeing if these ideas can work safely in people. But hitting the delete button on aging isn't as simple as taking a pill. The biggest challenge, the final boss in this video game, is cancer. The very things that cause us to age are also, in a weird way, protecting us from cancer. For example, the process of our telomeres, the protective caps on our chromosomes, getting shorter over time, acts as a natural brake on how many times a cell can divide. This stops cells from dividing forever, which is exactly what cancer wants to do. So while therapies to extend telomeres might make our cells live longer, they could also increase one type of risk for cancer that would need to be very carefully managed. The same kind of trade-off applies to our stem cells. To live forever, you'd need your stem cells to be constantly repairing and replacing old tissue. But a stem cell that can divide forever shares some dangerous similarities with a cancer stem cell. Indefinite life requires indefinite cell division, and that puts you on a razor's edge with cancer. To truly stop aging, you couldn't just fix one thing. You'd need a cocktail of therapies that addresses all the hallmarks, all at once, all the time, all while keeping that risk of cancer perfectly in check. It would require a level of biological control that's still science fiction, but it's a fiction we're getting closer and closer to writing. Let's just imagine we do it. We exorcise the ghost. We find the combination of therapies that stops, or even reverses, aging. Humans no longer die of old age. We've cured it. What does that world actually look like? It might not be the paradise you're thinking of. First, let's think about the Great Stagnation. The physicist Max Planck once joked that science advances one funeral at a time. New ideas often win out, not because their opponents are convinced, but because they eventually die off. Now, imagine a world where the old guard never leaves. Imagine CEOs, politicians, and cultural leaders staying in power, not for decades, but for centuries. Would society freeze? Would new ideas ever get a chance when the same unchanging ideologies are in charge forever? Then, think about what it would do to our most basic human experiences. What does "till death do us part" mean when death isn't on the table? Would people have 200-year marriages or a series of dozens of relationships? The whole idea of generations would dissolve. Wealth and property, instead of being passed down, could be hoarded by the same people for centuries, creating an economic gap between the anciently rich and the perpetually young that makes today's inequality look tiny. But the most terrifying idea isn't stagnation or 500-year-long careers. It's the birth of the ultimate inequality. It's almost a guarantee that a cure for aging wouldn't be available to everyone at once. It would be incredibly expensive, accessible only to the super rich. For the first time in history, humanity could split into two different kinds of people: the mortals, who live and die as we always have, and the ageless, who have bought their way out of a fundamental rule of nature. This kind of biological caste system could create divides so deep they could tear our world apart. How could a society work when one group watches their children and grandchildren grow old and die, while they themselves don't change? This isn't just a difference in money. It's a difference in what it means to exist. The fight for access to this technology could become the defining conflict of our future. We started with a question. Why do we age? The answer is buried deep in our evolutionary past. Aging isn't a mistake. It's a feature, the ghostly echo of a trade-off that helped our species survive at the cost of the individual. Evolution doesn't want you to die. It is just coldly indifferent to you living forever. Your eventual decay is simply the bill coming due for your ancestors' vitality. For all of history, that was just a fact of life, but we are the first generation standing on the edge of changing it. The science of longevity is moving from asking if we can treat aging to asking how. The tools to edit our own biology are being built in labs right now, but as we set out on this quest to kick the genetic ghost out of our machine, we have to face the enormous questions waiting for us. In our search for eternal youth, are we building a paradise of endless potential? Or are we accidentally engineering a permanent and deeply unequal prison for humanity? We might be on the verge of conquering death, but we have yet to prove we can survive immortality.